Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this next section of the course, we are going to study yet another famous deep reinforcement learning algorithm known as A3C. A3C stands for Asynchronous Advantage Actor Critic. As you can see, this term has 3 A's in it and 1 C, hence the abbreviation A3C. What's pretty nice is we've already done most of the groundwork for this algorithm. In fact, there's nothing new in terms of theory that we have to discuss. In particular, we've covered everything you need to know already in the section on policy gradients. As you may recall, the final form of the policy gradient algorithm we used was called actor critic, where the actor was a neural network that parameterized the policy, and the critic was another neural network that parameterized the value function. As you may recall, the advantage is just the term we use to measure the difference between the actual return at state S and the value at state S. In other words, it's how much better the action we took is relative to what we currently believe the value is. So now we know where the terms advantage and actor critic come from. First, let's review more closely how policy gradients work. As you recall, we're going to have 2 neural networks, the policy network and the value network. We can imagine that the policy network outputs pi, the policy, and the value network outputs v, the value. These networks have the weights theta p and theta v, respectively. The objective for the policy is derived by sort of working backwards from the actual policy gradient itself, or in other words, taking the integral of the gradient. This is just the return, g, minus v of s, multiplied by the log of pi. Notice I've represented it as the loss here, or in other words, something to minimize rather than maximize, since that's what we'll be using in TensorFlow. On the other hand, the value network loss is simpler. It's just the squared error between the return and the predicted value. Then during training, all we need to do is loop through each step of the game, sample an action, and then update the weights of both neural networks as we can see in this pseudocode. So the pseudocode is as follows. While we are not done, we sample an action from the policy network. We get A. Then we perform the action A in the environment and we get S prime and R. We set G equal to R plus gamma times V of S. We calculate the policy loss and the value loss. Finally, we perform gradient descent to update theta p and theta v. One minor difference between this and A3C is that we're going to take n steps at a time, which means we can use the n-step return rather than the TD return. So here we see another opportunity to combine the different things we've learned in this course previously. Another minor difference is that we are going to regularize the policy loss by adding the entropy as a regularization term. If you recall, the entropy of a distribution is the sum over all events of the probability of the event multiplied by the log probability of the event. In our case, the k's just represent the different actions, and pi of k is just the probability of that action at the output of the policy network. In the end, we take the usual policy gradient loss and add the entropy multiplied by a regularization constant, which controls the strength of the regularization term. In practice, what this does is it encourages exploration. If you recall, entropy is somewhat like variance in that it measures the spread of a distribution. We get the maximum entropy when each event has equal probability, and we get zero entropy when all the probability goes to a single event, or in other words, the outcome is deterministic. So using entropy as a regularization term allows us to fight between those two extremes. One extreme being that all actions are equally probable, and the other extreme being that only a single action can ever be chosen for a given input state. Another big improvement with this algorithm is that we'll now be able to incorporate neural networks as our function approximator. Specifically, we'll be using convolutional neural networks, just like we did for deep Q learning, to process the frames of the screen of an Atari game as input. One thing to note is that for vanilla policy gradients, this approach didn't seem to work. You'll see that with A3C, we are now able to use neural networks, and later in this lecture, we'll explain why that's the case. So what makes A3C interesting is that it's asynchronous. In other words, what it does is take the algorithm we had before, but make it so that it's an asynchronous algorithm. In the rest of this lecture, I'm going to explain to you exactly what that means. First, in modern computing, what we often like to do is run things in parallel. So for example, suppose I had a for loop over 1 million files that I need to do some processing on. Well, in code, this is very simple. I can just loop over all 1 million files and run my function on each file. But this process is slow. If I have 2 million files, the time it takes for this code to run just doubled. So what can I do? These days, a popular method is to use multiple machines. So I can have 1,000 CPU cores, each responsible for 1,000 different files. In this way, I've reduced my computation time by a factor of 1,000, minus any overhead for coordinating each worker machine. But we don't even have to go that far. As you might already know, your computer, if it's reasonably modern, already has multiple cores which can run code in parallel. So while you might only have one machine, you can still take advantage of the multiple cores that exist inside it. So what is the basic algorithm for A3C? Conceptually, we're going to have one set of master networks, one for the policy and one for the value function. You can think of that as a set of global networks. Now, every so often, this global network is going to send its weights to a set of worker machines, each with their own copy of the policy network and the value network. Then, each of these worker machines is going to play a few episodes of the environment using its current network weights. From its own experience, each worker can also calculate the policy gradient updates, as well as the value function updates. Now, of course, keep in mind that only this worker knows about its own updates. Finally, the worker sends its gradients to the global networks so that the global network can update its parameters. And every so often, the global network gives its new updated parameters back to its worker machines. So worker networks are always working with a relatively recent copy of the global network. So why is this good? Well, firstly, now the global master network has no work to do. It's not going to be involved in actually playing the environment. Only the workers do that. So the workers, hence their name, are doing all the work. They play the episode, calculate the errors, and find the update gradients. The global master network is the beneficiary of these updates. And of course, since the global master network has multiple workers playing episodes, it can gather a lot more experience in parallel than it could have by playing the environment by itself. Long story short, we save time. But there's another big advantage to doing things this way. Remember that there's always some randomness in each game. Each game isn't going to start the same way, and each action sampled from a probabilistic policy will vary. So every game that the workers play is going to be different. If you recall, sometimes in reinforcement learning, the performance of our agent can drop off sharply due to a bad update. By having multiple workers contribute to the global master network, we can reduce the variance of our updates and have a more stable learning trajectory. To state this another way, what we achieve by having multiple different workers play different episodes with the same parameters, we achieve more stability. This is like, say, instead of doing stochastic gradient descent, where you look at one sample at a time, you can do batch gradient descent, where you look at several samples at a time. As you may recall, this makes the loss per iteration much smoother. This might also remind you of the Deep Q network section, because in that case, we also wanted to add different features that helped us stabilize learning. In particular, that involved techniques like freezing the target network and using an experience replay buffer. Using an experience replay buffer allowed us to look at multiple examples during each training step, which is a little bit like batch gradient descent, and so intuitively we understand how this helps us stabilize learning. In short, stabilized learning is good, and we can achieve that by looking at multiple samples at the same time. It just so happens that with A3C, the way that we do this is by having multiple parallel copies of our agent playing the game. This is what allows us to make use of neural networks as our function approximator, whereas they don't work well with vanilla policy gradients without parallelization. In other words, Deep Q networks and A3C both try to solve the same problem, which is how can we make use of neural networks in classic reinforcement learning algorithms? They just happen to do it in different ways. In the rest of this lecture, we're going to discuss how the code is going to be structured. Remember that the actual algorithm we'll be using is nothing new. It's just the same old advantage actor critic that we saw before. The difference now is that we want to have concurrent agents that asynchronously copy and update their parameters. So the way the code is structured is this. We're going to have 3 files. The first file is main.py. This is sort of the master file, which is going to be responsible for creating the master global policy network and value network. It's also going to coordinate the workers. In other words, it's going to create a handful of workers, each with their own thread, and then wait for them to complete. The second file is worker.py. As you can tell by the name, this is going to contain all the classes and functions that make up the worker. Each worker is responsible for creating its own version of the policy network and value network, copying the weights from the global networks, playing episodes of the game, and calculating gradients to be sent back to the global network. Finally, the third file is nets.py. This contains the definitions for the policy network and value network. In the next few slides, we'll be looking at the pseudocode for each of these 3 files. Oh, and by the way, you can find these files in the folder A3C. In the first file, main.py, the basic structure is this. First, we're going to instantiate our global policy network and our global value network. Then we're going to count how many CPUs are available and create that many threads with one worker object for each thread. We're also going to create a global thread safe counter that's going to tell us when to quit, since we're going to go up to a maximum number of steps. You'll see exactly how that works in a later lecture. In the second file, worker.py, the basic structure is this. We're going to have the run function, which is going to be run by each thread. The run function just runs a simple loop. First, we copy the parameters from the global network to our local copy of the network. Then we run n steps of the game. At this stage, we store all the data we need to pass into our neural network, such as the states we encountered and the rewards. Then we update the parameters of the global network using the gradients from the last n local steps. To give you an idea of how this might work, we can think of it in terms of these equations. The first step is to calculate the gradient, which is the local cost with respect to the local weights. The second step is to update the global weights using gradient descent with the local gradients. Now, of course, in TensorFlow, it's not going to look exactly like this because we don't actually explicitly write out the gradient descent update. Instead, we'll be using an adaptive training algorithm such as RMSprop, and our actual goal will be to figure out what is the correct TensorFlow function to apply this sort of mixed update where the gradient used to update the weights of one network actually comes from the loss of another network. The worker.py file is probably going to be the most complicated of the three, so you just have to wait and see what the exact details are. Just keep in mind each of the above steps will actually turn out to be multiple functions. The last file we're going to discuss is nets.py. This more or less just implements the policy network and the value network, although there are some important details to talk about before we dive into the code. First, these networks are going to be convolutional neural networks, which means they're going to consist of a series of convolutions followed by a series of fully connected layers. In addition, both networks are going to share a common body. In other words, only the last layer of each neural network is going to be different, and all the preceding layers will have shared weights. Conceptually, you can think of this as a two-headed dragon. I'm not going to go into too much detail now about how this is implemented, but in TensorFlow, we'll want to make use of variable scopes and an argument named reuse, which tells TensorFlow to use the same weights that were already created. In the next few lectures, we'll look at this code in depth. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, my goal is to give you an overview of how threading works in Python, since many of you haven't seen this before. Essentially, this example will have the same basic structure as our real example, except each worker is just going to count and print out its count, up to a global maximum. The relevant file for this lecture is threadexample.py in the A3C folder. First, let's talk about the worker class. So remember that conceptually, what's going to happen is that we're going to create multiple of these, and they are all going to run in parallel. In the constructor, I have two input parameters, the worker ID and a global counter. Inside the constructor, I'm also going to create a third variable, a local counter. So the idea behind this very simple program is this. I want to have a global counter that's shared amongst each thread. Each thread is going to run in a loop, and each iteration of the loop, it's going to increment the global counter. Once the global counter reaches 20, all the threads are going to terminate. The trick is, each worker is going to take a different amount of time between each iteration of the loop. So what that means is, if say I have two workers and they're jointly counting up to 20, then one of the workers might have been responsible for incrementing the counter 13 times, whereas the other worker might have been responsible for incrementing the counter only 7 times, but the total is 20. So that explains what we have next in the run function. The run function runs in an infinite loop. The first thing we do is sleep for a random amount of time, anywhere between 0 and 2 seconds. Then we increment the global counter. We also increment the local counter. Next, we print out the worker's ID along with its local count. Finally, we check if the global count is greater than or equal to 20, and if it is, we break out of the loop. So what might we expect when we run this? Well, let's suppose we have 8 workers. Our total count is 20. So on average, our count will go up to 20 divided by 8, which is equal to 2.5. In reality, some threads might only count up to 1, but other threads might count up to 4 or 5. Let's now go over the main part of this script. The first thing I'm going to do is create a variable called global counter, which is a thread-safe iterable. This is just going to count, so 0, 1, 2, 3, and so on. But it's thread-safe, so when one thread updates the count, all the other threads will know about it. Next, I'm getting the number of available CPUs by calling multiprocessing.cpu_count and assigning that to a variable called numWorkers. Next, I have 3 main blocks. The first block is to create the workers. The second block is to start each thread, and the third block is to join each thread. We'll talk about why join is needed later. So in the first block, all I do is create a list of workers. I loop through num workers, so that's going to start counting from 0, and I'm going to use that as the worker ID. Each worker constructor also gets the global counter passed in. Finally, I append each worker I create to my workers list. In the second block, I create a list of worker threads. So now I loop through each worker and make a lambda function from each worker's run function. This is because I want to end up with a function that doesn't have any parameters. Next, I create a thread, and I pass in the function name I just created. The thread now knows to call this function. Once I create a thread, I call the start function to launch the thread. So that's going to call the worker's run function, but now each worker's run function is going to run in parallel. Finally, I append the thread to my list of threads. The last block we have is the join block. So why do we need this? Well, normally when you have a thread, you can think of it conceptually as sort of outside the main program. In other words, my main program will launch some thread, but it doesn't care what happens with the thread after that. So once I launch the thread, I consider my job done and I can move on. In terms of this code, I'm going to print out done at the end when everything is complete. But I can't do that because launching a thread is not the same as waiting until the thread is finished. Therefore, I don't want to launch my threads and print out done while the threads are still running. Instead, I only want to print out done when all the threads have completed their jobs. So that's what join is for. We'll demonstrate this code twice, both with and without join. So let's run this with join first. So as you can see, we print out done at the end as expected. Also note that the final count for each worker is different. That's because they're all waiting for different amounts of time. So some count up to 4, whereas others just count up to 3 or 2. Now let's run this same script without join. As you can see, done gets printed out at the beginning, which of course doesn't make any sense. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, now that you understand how basic multithreading works, we're going to start looking at the actual A3C code. The first file we're going to look at is main.py. At the top we have most of our usual imports, such as NumPy, Matplotlib, and TensorFlow. For threading, we'll also want to import the threading module and the multiprocessing module. From our nets.py file, we're going to import a function called createNetworks, and from our worker.py file, we're going to import the class worker. Next, we're going to define some constants. First, we have our environment. So while A3C works on multiple Atari environments as well as some non-Atari environments, we're going to stick with breakout, since that's what we've tuned the hyperparameters for. We're going to set max global steps to 5 million. This is just like our previous basic threading example, where we had a total number of combined steps for each worker to do. Finally, we have a variable steps per update. This is going to be the number of steps each worker performs before calculating the gradient and sending it back to the global network. Next, we have an environment function, which just makes it a little more convenient to create our environment. We'll be using this multiple times, which is why this is useful. Next, we're going to manually set the variable numActions. Remember that breakout is kind of annoying in this way, where the environment contains actions that actually don't correspond to actual actions in the game. So while the real number of actions is 4, it's going to return 6. The Pong environment does this also, So for breakout and Pong, we're going to set the number of actions manually. Next, we have the smooth function. As you know, the total return at each episode is going to vary by a lot, so the final plot of each return per episode is going to be very noisy. In order to smooth out some of this noise, so that we can see the overall trend more clearly, we're going to take the moving average of the returns with a default window size of 100. Next, we're going to get numWorkers, which is the number of workers we're going to create. To get this number, we'll call multiprocessing.cpu_count. The first thing we're going to do inside the with block is create a TensorFlow variable called global step. Now, if you look closely, one thing you might realize is that it looks like we're not going to use this variable anywhere. Internally, however, TensorFlow requires this for some of the computations we're going to do. So if you try to remove this, your code should actually break. Perhaps this is just bad design on TensorFlow's part. Next, we're going to create our global value and policy networks. To do this, we're going to use the scope called global. As you can see, both of these networks are returned in one function call, create networks. You'll see why that's convenient later in the code. Next, I'm going to create an iterator called the global counter. This is just like the one we had in our basic threading example. It's going to make sure that we only go up to a predefined number of combined steps. Next, we create a returns list variable, which is going to store the returns achieved by each individual worker. This is what's going to keep track of the performance of our algorithm. Remember that when you pass a list into a function, it gets passed by reference, so each worker is going to be updating this same list. So this returns list is a global variable, which all the workers have access to. And since we're only appending numbers to the list should be thread safe. Next, we're going to create our workers. This is again essentially the same as we had in our basic threading example, just that these new workers have more arguments. So we're going to pass in a worker name, which is just the string worker concatenated with a number, the environment, the global policy network, the global value network, the global counter, the returns list, the discount factor gamma, and the maximum number of global steps. Hence, the worker knows when to quit by checking the global counter and comparing it to the maximum number of global steps. Next, we're going to start a TensorFlow session and launch our workers. As usual, we have to start by running the global variables initializer. Then we have something new, which is TensorFlow's coordinator object. The coordinator object helps us to coordinate the termination of the threads. You'll see that this is like the join function we used in the previous threading example. Next, we're going to loop through each worker and create a set of threads that calls each worker's run function. Once we've created the thread, we start the thread and add it to our list of threads. Outside the loop, we call the coordinator's join function on the worker threads. Notice how this lets us set a grace period. Basically, each thread is going to try to stop at some point, and at that point, they have 5 minutes to actually terminate. If they don't terminate by the end of the grace period, the coordinator will raise an error. Finally, the last thing we do in this script is plot the returns we collected. In addition, we're going to plot these smooth returns, so you can see more clearly the improvement over time. In the next few lectures, we'll look at the other files for this example, nets.py and worker.py. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we're going to look at the code for nets.py. This code is relatively simple compared to the other files in this example, since it only involves building neural networks, which we already know how to do. The most challenging part of this will be to get the policy network and value network to share their parameters. So the first function we have is for building the body of the neural network, called build feature extractor. You won't be able to tell just by looking at this code, but this will allow us to share these layers between the two networks. So this is going to be a standard convolutional neural network. First thing we want to do is scale the inputs to be between 0 and 1 by dividing by 255. Next, we pass the input through two convolution layers. Then we flatten the data and pass it through one fully connected or dense layer. So pretty basic LeanEd style architecture. Next, we have the policy network class. In the constructor, we're going to take in the number of actions as the number of outputs and a regularization constant. Next, we're going to create our placeholders. The first placeholder is our input data, which is, just like with deep Q networks, a sequence of 4 consecutive grayscale frames. The second is the advantage placeholder, which will contain a batch of advantages. The third placeholder represents the actions that were selected for each of the input states. As you may recall, this is all the same as we discussed in the policy gradient section. Next thing we're going to do is pass our inputs into the body of the neural network. To do this, we're going to create a scope called shared and set the reuse argument to false. Take special note that this is false, since it'll become relevant later in this lecture. So we call build feature extractor, and we get out a variable called fc1. The next thing we want to do is pass fc1 through the rest of the neural network. For us, this is just a single final dense layer, which maps to the action space. More precisely, we're going to get the logits for each action, after which we can apply the softmax to get the probability for each action. As usual, the next thing we need to do is build up our cost function and then create our minimizer. Of course, creating the minimizer is not so simple in this case because we know that the gradients for the worker networks will be used to update the global network, but more on that later. In terms of the output and cost, there are still a few things we have to do. First, we need a way to sample an action, given the output of the neural network. Luckily, TensorFlow already comes with a categorical distribution object, which accepts logits as input. We can create a TensorFlow tensor called sampleAction, and then use that later to sample actions. So that's what we're going to use when we're playing the episode. Next, we have the entropy term, which acts like regularization for our model. Next, we need to select the probabilities for the actions that were actually selected. Unfortunately, this isn't as clean in TensorFlow as it would be in Theano, but we can still make it work. As always, you can always explicitly output NumPy variables at each step in order to get a better idea of how each operation works. Finally, from the selected action probabilities and the entropy, we can calculate our loss. The next thing to do is write some code to help us minimize this loss. First, we're going to create the RMS prop optimizer, and then we're going to use it to compute the gradients for each variable in our network. Next, we're going to do something which is unusual that you won't see in our normal single-threaded scripts. Instead of calling the RMS prop minimize function, we're instead just going to get the gradients and their corresponding TensorFlow variables. And for now, all we're going to do is store this list as an attribute of the network. You'll see how these are used later when we actually do the update. Next, we have the value network, which is largely the same thing, except it predicts the value function. First, we only have two placeholders, one for the input states and one for the target values. As before, we have 4 consecutive grayscale frames for the input. Next, we're going to create the initial layers of the neural network. Importantly, we are again going to use the scope shared, but now we're going to set reuse equal to true. This is important because previously we set reuse equal to false. That means when we call this function build feature extractor, it's going to use the same variables we created previously. In other words, it's going to share the weights for those layers between these two networks. And so this effectively makes the body of the neural network shared between the value and the policy, just like we discussed. Next, we create the final layer of our value network, which is just a fully connected layer with one output. We'll call this v-hat. We also need to convert this into a one-dimensional tensor, so we use the squeeze function. Next, we're going to calculate the loss, which is just the squared error between v-hat and the target. Finally, as before, we're going to create an RMS prop optimizer, but instead of calling the minimize function, we're simply going to obtain a list of each variable and its corresponding gradient and store these as an attribute of the object. The last piece we have in this file is a function called createNetworks. So the way this is structured is that to create a policy and value network, the other Python files should only use this function. They should never individually create a policy network or value network. And the reason for this is the policy network always has to be created first, since it sets reuse equal to false, whereas the value network sets reuse equal to true. So in order to avoid ambiguity, any outside code wanting to create policy and value networks can use this function. In the next lecture, we'll look at the final code file in this example, worker.py. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we're going to tackle the final piece of this puzzle, which is worker.py. The worker is essentially what lives inside each thread, and so it does a majority of the work, hence its name. To begin this lecture, I want to first discuss what this file is supposed to do at a high level before jumping into the code. So this is going to help you anticipate everything we see in this pretty long lecture. Remember that the worker is what runs in the thread, so there are going to be multiple workers running in parallel. We know that each worker has to have its own version of the policy and value networks, and therefore the worker has to be able to copy the current weights from the global networks over to its local networks. So we're going to have some kind of function that copies the weights from the master policy and value networks over to the worker's version of those networks. In addition, we still haven't discussed how we're going to update the weights of the global networks. Recall that the gradients are going to be calculated for the local networks, and these gradients are going to be used to update the global networks. So that's another function we have to write, something that updates the global networks using the local gradients. We also need some other basics, such as a function to convert the images from the game into grayscale and downsample them. Then we need a function to concatenate 4 consecutive frames from the game into a single array. So that's what's going to be the state to our neural networks. We'll also need a way to group each step of the game together. So that's going to keep track of the state, action, reward, next state, and whether or not the episode ended. We can use this object to then form the inputs and targets to update the weights of our neural networks. So that's just a short summary of everything the worker has to do. So now let's get to the code. At the top, we have all our usual imports, as well as create networks from nets.py. The first thing we're going to do is create a class called step, which stores a step of an episode. This class doesn't have any functions, just attributes. So essentially, this is just for the purpose of data storage and organization. We want to keep track of the state, the action in that state, the reward, the next state, and the done flag. Next, we have the image transformer class. In the constructor, we're going to define the TensorFlow operations that need to be done in order to transform the image. The first step is to convert the image to grayscale using the function RGB to grayscale. Next, we're going to crop the image to remove the irrelevant parts. Finally, we're going to resize the image to 84 by 84 and squeeze the output to get rid of redundant dimensions. In the transform function, we run the above operations in a session and return a NumPy array. Next, we have some useful functions for creating states out of each frame we collect. First, we have a function called repeat frame. The reason we need this is because when we begin an episode, we're only going to have one frame. But in order to build a state out of it, we need 4 consecutive frames. So what we do is just repeat the same initial frame 4 times. That will be our first state. The next function, shift frames, takes in a state along with the next frame to build the next state. Basically, all this does is removes the oldest frame from the state and then concatenates the next frame to the other end. Next, we have a function called getCopyParamsOp. When we copy the weights from one network to another, we can express it in terms of TensorFlow operations, which is what this does. So we're going to take in a list of 2 sets of variables, the source variables and the destination variables. In order to make sure they appear in the right order, we're going to sort them by name. Then we're going to use TensorFlow's assign function to represent each copy operation. Finally, we're going to return a list of these operations. Next, we have a function called makeTrainOp. So normally, when we have a TensorFlow optimizer, we just call the minimize function, and that's our trainOp. But in this case, we need to do something special because we're using the gradients of one network to update the weights of another network. So this function takes in a global network and a local network. The first thing we do is get a list of the local gradients. Then we clip the gradients to have a maximum norm of 5. Then we get a list of variables which come from the global network. And then we combine the list of variables and corresponding gradients into a single list called local grads global vars. And now this is in the right format to pass into the function which actually updates the weights. So we call the function applyGradients, which belongs to the global nets optimizer. We pass in the list we just created and also a global step variable, which, if you recall, we defined earlier. Next, we have the worker class. As we discussed earlier in main.py, it takes in the following arguments: name, which is its name; environment, which is an environment object; policyNet and valueNet, which are the global policy network and value network; global counter, the returns list, the discount factor, and the maximum number of global steps to take. Next, we assign all these inputs to the attributes of the worker, and we also assign the TensorFlow global step, as well as create an instance of the image transformer class. The next thing we want to do is create local versions of the policy network and the value network. So we just call the createNetworks function, which we've used earlier. Note how we can use the worker's name as the scope since it's going to be unique. Next, we call the function getCopyParamsOp, which we made earlier, and we just save this op to an attribute of a class. The first set of variables we pass in are the global variables, and the second set of variables are the local variables. And therefore, this function is going to be used to copy the weights from the global networks to the local networks. Next, we're going to call makeTrainOp, which we created earlier, on both the value network and the policy network. So we have 2 train ops, one for each network. Finally, we have a state attribute which keeps track of the current state, total reward attribute which keeps track of the total reward, and an attribute returns list which just refers to the global variable returns list. Next, we have the run function, which, as you recall, is what's going to be run by the thread. As you'd expect, this is just a loop. So to start, we're going to reset the environment, get the first frame, transform it, and then repeat it 4 times to get the first state. Then we're going to enter the loop. As you can see, we use the coordinator we created earlier to control when the loop stops. The first thing we do in the loop is copy the weights from the global networks to the local networks. So our worker is always working with a relatively fresh copy of the master network's weights. Next, we run n steps of the environment. This just calls a function called run n steps, which we will look at shortly. And this function returns 2 things: a list of step objects called steps, which, as you recall, contain all the information about states, actions, rewards, and so forth, as well as the global step counter. Next, we check if the global step counter is greater than or equal to the maximum number of global steps we want to take. If it is, we call request stop on the coordinator, and then we return to exit the run function. This, by the way, is how all the other workers running in parallel also know when to quit. Next, we have the update function, which is actually going to pass in the data we collected during our n steps, take the gradients, and update the global network. So that's the main loop that's going to be running in each thread. Next is just some functions that are going to be called by the run function. First, we have the sample action function. This just takes in a state, passes it into the policy network, and returns an action sampled from the output. As you recall, we always work in batches, so we're effectively working with a batch size of 1, and we want to grab the 0th output. Next, we have the getValuePrediction function. So whereas the previous function gets a prediction from the policy network, this will of course get a prediction from the value network. As before, we're working with a batch size of 1, so we want to grab the 0th output. Next, we have the run n steps function, which we saw being used earlier. As its name suggests, this function is going to run n steps of the environment. Although there is one exception to this, which is if the episode ends, in which case we'll return early. So the first thing we need to do is initialize an empty list of steps. Then we do a for loop n times. Inside the for loop, we use the current state, pass it into the policy network, and sample an action based on this current state. Then we take this action in the environment. We get back the next frame, the reward, and the done flag. Next, we call the shift frames function to get the next state by adding the current frame to the existing state and removing the oldest frame. Next, we check whether or not this is the end of an episode. That means the done flag is true. If we are done, then we can print the return for this episode along with the worker's name. Then we append the return to our global list of returns. And to help us debug, we're also going to print out the average reward for the last 100 steps every 100 steps. So that's what that looks like. This is going to help us see whether or not the agent is improving over time, since each individual return may vary by a lot. Then we reset the total reward variable to 0. If the done flag is not true, then we simply add the current reward to the total reward, which is how we're going to keep track of the total reward for each episode. Next, we would like to save the step we just took. To do this, we're going to create a step object, which, as you recall, stores the current state, the action, the reward, the next state, and the done flag. Then we append this step to our list of steps. Next, we increment the global step variable. As you recall, the worker always checks this to determine when we should quit. So all the workers are going to be incrementing this same global step within their own threads. Next, we want to update the current state, which is stored in the attribute self.state. So if the episode is done, then we simply reset the environment and repeat the initial frame 4 times. If the episode is not done, then we set self.state to the next state. Finally, we return our list of steps and the global step counter. Alright, almost done. The last function in this file is the update function, which, as you recall, we made use of earlier. At a high level, this function is going to build up the inputs and targets for our neural networks, and then it's going to call the train ops we defined earlier. To recap, here are the quantities we need. First, we need the state at each step, since that's the input into both the policy network and the value network. For the value network, the target is of course the return. For the policy network, the loss is a function of the advantages and actions that were taken in each state. The advantage is, as you recall, the return for the input state minus the predicted value for that state. Now we're going to do a little trick here, which involves making use of what we learned in the end step section. As you recall, normal temporal difference learning uses a one-step ahead prediction in order to measure the return. So with TD learning, we would always use R plus V of S prime as the return. And that would make R plus V of S prime minus V of S the advantage. But since we've taken n steps, that means we can make use of the n rewards that we collected. And making use of these n rewards makes our prediction of the return more accurate. So if you imagine we've taken 3 steps, so we have the states S1, S2, and S3, and the rewards R1, R2, and R3, then we can calculate the returns as follows. So the return for S3 will be R3 plus V of S4. Now here I've removed gamma just so you can more easily see the pattern. The return for S2 will be R2 plus R3 plus V of S4. And the return for S1 will be R1 plus R2 plus R3 plus V of S4. So in other words, we only need to make a prediction for the very last state value. Of course, if the last state is a terminal state, then the value is 0, so we set the initial reward variable to 0. Otherwise, we set it to the value of the final next state. Next, we accumulate the data for our training batch. Since we're going to multiply gamma to the future returns recursively, we're going to loop through each state in reverse. In the loop, we're going to update the value of the return, which I've slightly misnamed here as reward. From this, I can calculate the advantage, which is just the return minus V of S. Finally, I can append the state to my list of states, append the action to my list of actions, append the advantage to my list of advantages, and append the reward to my list of value targets. Next, I create a feed dict to pass into my Tensorflow session. These are essentially just all the placeholders I defined for our neural networks earlier. And the final step is to do a session.run on the TensorFlow global step variable, the losses, and the train ops. Technically, you don't really need the losses, but you could plot them in order to understand the progress of your model training procedure. So that's everything for this code. Let's run this and see what we get. Okay, so you can see that not only do we do quite well, we achieve this in a much shorter amount of time than we did with deep Q networks. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to summarize everything we learned in this section. A majority of this section was just code because we already learned all the theory we needed in the policy gradient section. The only minor difference in theory is that we use the n-step return instead of the TD return. To recap, we learned how we could have a bunch of workers learning in parallel by using multi-threading. In terms of theory, this allows us to add stability to the training algorithm because we're essentially taking the average result from a bunch of different random episodes. You hear that word a lot in reinforcement learning. The concept of stability is very central. This is mostly because stability is what is lacking. That's why we can't simply plug in a neural network into a Q-learning function approximator and expect it to work. That's why we can't plug in a neural network into the vanilla policy gradient algorithm either. And that's really the major theme of this course. Since merely plugging in neural networks into existing algorithms causes instability, then what can we do to make things more stable? With deep Q learning, that involved creating an experience replay buffer and having a target network that didn't change too often. With A3C, that involves having multiple workers playing different episodes in parallel. At the same time, one big hurdle in reinforcement learning is hyperparameter search. So even if your algorithm and your code is sound, if you choose the wrong hyperparameters, your agent simply won't perform well. In other words, lots of resources, both in terms of compute and your own time and effort, are needed in order to really determine whether or not an algorithm works. Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to summarize everything we've done in this course. It's been a long journey to this point, because not only have you had to study deep learning, but you've had to study reinforcement learning as well. This course was about combining these two techniques, and also a little bit about expanding our knowledge of reinforcement learning. I tend to think of this as applying deep learning to reinforcement learning, rather than the other way around. Deep learning is more like a general technique that can be applied to supervised learning or unsupervised learning as well as reinforcement learning. But reinforcement learning is an entirely different paradigm, where we have an intelligent agent trying to maximize its reward in some environment. So what did we learn in this course? Well, we started this course with a review of some basic techniques in both reinforcement learning and deep learning. We looked at Markov decision processes and the three ways of learning how to solve MDPs: dynamic programming, Monte Carlo methods, and temporal difference learning. Next, we looked at the OpenAI Gym, which provides us many environments for practicing reinforcement learning. This is especially valuable because coding our own environments would be extremely time-consuming and completely unrelated to reinforcement learning itself. This allowed us to practice the reinforcement learning techniques we just reviewed and to practice using Theano and Tensorflow, which are very helpful because of their automatic differentiation capabilities. They let us build arbitrarily complex neural networks, and the update equations are all automatically generated from the structure of the cost function. Also in this section, we looked at a special type of neural network called the Rbf network. Unlike our usual deep neural networks, these networks are shallow and use fixed feature representations. That means features won't be learned using gradient descent. Next, we looked at n-step methods and TD lambda. We saw how these are both ways we can do something that's kind of in between Monte Carlo and TD learning. Whereas n-step methods are discrete, the lambda in TD lambda is continuous and between 0 and 1. Now, of course, there's nothing that makes these better or worse than the existing reinforcement learning methods we learned about. They are just new hyperparameters to be chosen. Next, we looked at policy gradient methods. This gave us a totally different way of solving reinforcement learning problems. Instead of making the policy just greedy or epsilon greedy with respect to Q, we parameterize the policy itself. In this situation, we parameterize both the policy and the state value function v of s. Parameterizing the policy is interesting because it allows us to easily handle continuous action spaces, as we saw with continuous mountain car. The only change we had to make was, instead of modeling the output as a discrete distribution, we modeled the output as a Gaussian. Lastly, we looked at deep Q learning. Deep Q learning is just the combination of deep learning with reinforcement learning. Initially, deep learning looks like a pretty attractive option in reinforcement learning because we already have the theory behind approximation methods, and neural networks are function approximators. So a naive approach would be to just plug in a neural network. Of course, this doesn't work, so we learned about new techniques to make it work. In particular, we looked at experience replay using a target network and combining previous data into the current state in order to model motion. Now, of course, this isn't all there is to deep reinforcement learning, since new stuff is being invented all the time. Could new material be added to this course? Most certainly yes. I love giving you guys free updates to my existing courses and making them better over time, so feel free to use the Q&A to make recommendations. Thank you for taking this course, and I'll see you next time.